We've played around with this little movie before. It's kind of interesting, I think. The jet level, whatever, which if you have $120,000 hanging around that you're not using at the moment, then you can purchase one. I think that's what it is. Well, you see how it works. It has a jet on each side, so it's stabilized, so you have some control over it. You've got hand grips to be able to change the intensities of jets, I suppose, in some way, and you can move it relative to your body. It's an umbilical, which is a tube which attaches to some power plant, which tows behind it, which you don't see in any of these. It looks kind of magic, but it's just a raft that's being pulled behind, I think. I actually can't see, yeah, the raft, that white thing being pulled behind is the raft with the power plant in it. Apparently this, they've taken it from LA to Catalina Island. That crossing is about 26 miles or so. And so what I thought we'd do today is try and solve that problem. So one question you might ask is, what size pump do you need to be able to do that? And we have most of the information to be able to do that. And so maybe that provides a useful focus for us to be able to point our attention to be able to try and do that. Okay? And so we've been talking about pipe flow. We know that the major portion, the major component of pipe flow for later items, major component of pipe flow is being able to write the one-dimensional energy equation, which looks just like Bernoulli equation. We talked about the components of that. And the important parts of it, well, I'll just write it out. We have to write it from upstream to downstream, you know. These alphas are about 1. We have a pump head within the system. And the left-hand side is upstream, sorry. And the right-hand side is downstream. So this is, you know, you should remember these expressions, this one anyway, all the way through your careers, I think, because they are going to be of use to you. Plus 2 components, right? Sum of head losses major, and sum of head loss, sum of head losses minor. And so we need to be able to figure out what these terms are, and we made a start on doing that last time. We surmised that these we could get as some non-dimensional term, and the non-dimensional term was that individually the head loss for the major losses is due to flow along the individual components of the pipe. Pipe has some length, has some diameter, D, which we'll call it, has some roughness on the edge, and the magnitude of this roughness we'll call, and your book calls epsilon. Not doing a very good job with this. And together, this magnitude of head loss, which has to be in units that are equivalent to this, which are units of length, is defined as some kind of friction factor, which we talked about yesterday, which kind of links us to the Moody charts, multiplied by, it scales with how long the pipe is relative to its diameter. If you double the length for the same size pipe, you double the head loss. That makes sense. And it scales with the velocity, the kinetic head term. And so the things that we should remember are that this V should be the velocity in that pipe, not the velocity at the downstream or the upstream locations. And so, you know, we've drawn this thing before, right? Bless you. I don't know why we always draw upstream, downstream from left to right, but we do. And so that's the geometry we're dealing with. So the velocity is the velocity in that pipe or fitting. And this friction factor we get mainly by experiment by observation. And for laminar flow, which is for Reynolds numbers which are less than, say, 2100 or 2000. I'm not sure why 2100 comes in. And Reynolds numbers are defined as a velocity, a density, a characteristic length. Our characteristic length is always the diameter, just by convention. It makes sense you could scale, yeah, it's the only one that makes sense to scale it with. And I think, well, it might not actually be 2100. Let me just see. Yeah, it's of that order. So, well, let's see. What does it say earlier on in our stuff? I don't need to, just want to have it consistent. Yeah, all right. So this is this. So for Reynolds numbers less than that, then for a circular section tube, then it is merely the fact that this friction factor, squiggly f, is equal to 64 over Re. And that's for a circular section pipe. So that's important. That's only for that case. And for Reynolds numbers less than 4000, but greater than 2100, this friction factor is a function of what? It's a function of the Reynolds number and of the relative roughness. I'm just interpreting these charts for you. Actually, rather than going to the chart, let's just draw it. Whoops, that's not very good on the bottom, is it? So this is Reynolds number. This is friction factor. And so this here is 64 over Re. And then we have all of these behaviors beyond that. And so if you remember these different responses, what was going on? So this was for increasing roughness. Okay. And so as you get rougher pipes, you see two things. One, it goes to this nonlinear regime earlier at lower Reynolds numbers than it does for a smoother pipe. And so if you define these kind of boundaries, wish I had some different colors, but I don't. This is 2000. Well, let's call it 2100 since we said 2100. And this maybe is 4000. And so this is turbulent. This is laminar. And this is this mixed regime in between. And so the key features, I think, to get from this chart are that if it's laminar flow, and if it's a circular section pipe, and these are for circular section pipes, by the way, then we have just this one relationship. And ultimately it kind of goes down here in this regime and goes off the bottom of the chart. In the mixed regime, then you see that this slope, this graph, has a slope. And so it's not horizontal, but it has some kind of changing slope as it goes through this mixed regime. And what that means then is that the friction factor is a function both of the Reynolds number as you go horizontally, but also a function of relative roughness. Once you get in this fully turbulent regime, so for Reynolds numbers, say, greater than 4000, then the friction factor is really no longer, it's kind of a function of Reynolds number because you have to get beyond that threshold. But once you're beyond that threshold, it's only a function of the roughness, right? You're either on this line, which is horizontal, or this line, which is horizontal. The roughness doesn't change if the pipe doesn't change. And so it's kind of a function of Reynolds number, but we don't really have, it's a threshold Reynolds number, if you like. So you have to know if you're on the right side of this line, which isn't quite a vertical line as you see, they're kind of curved. So I'll come back. So that's the figure that we're representing. So I'm saying something quite simple in too many words. Laminar, only here. Mixed behavior, it's a function of Reynolds number and the roughness because these lines have curves to them. On the right-hand side of this, fully turbulent, it's only really a function of roughness because a rough pipe has a friction factor of this magnitude at all Reynolds numbers beyond this, or a smoother pipe has a friction factor of this number at all Reynolds numbers. And so that's really all I'm trying to say in that. Okay? So those are the key issues. And so that's the one property we need to know. And so we talked about that before. So that's just reaffirming what we know. We call them major losses because they're small per unit increment of pipe, but as you saw in the jet lev, the pipe's quite long. And so incrementally they add up. And so what we also need to talk about now is the contributing minor losses which add to this. So that's the recap. Moody charts are important for us. So far we're talking about circular section pipes, but there's no reason why we can't also look at pipes which have irregular sections, prismatic sections, square sections, you name it. And so there's nothing that we can't use the Moody charts for in some approximate way. Okay, so that's where we're going. Minor losses. Well, minor losses are the second term in the Bernoulli equation, so that we want to deal with. They're smaller incrementally. Actually, they're larger incrementally, but maybe there are fewer of them in the system. They're just the bends that you have. We've used them once before, I think, in some of the stuff that we were doing. Some of the examples I thought we did on the one-dimensional energy equation, which is what this Bernoulli equation is that we have on the top of the previous sheet. And we saw that they basically take this form. The head loss that we get is a function of, again, this velocity squared term. You'll remember that for the major losses, this term is equal to this. And so it's just, this is the dependent variable that controls the behavior, if you like. So it's no different from that. And all it is that instead of being a loss per unit length of pipe, it's just a single loss. You go through one fitting, you turn a right angle bend, you lose some energy because you're changing not necessarily the velocity, not necessarily the speed, but you're changing the velocity. So this is velocity as a speed, not as a vector, which has direction and magnitude. And so it needs to be the velocity in the fitting, of course, as indeed this is the velocity in the pipe, not the velocity at the ends where it comes out in Bernoulli, so you need to correct for that. And you can rearrange this in different ways. Typically, if you want to figure out what this loss coefficient is, you have a pipe, you put water along it at some flow rate, and you measure the pressure you have to apply between upstream and downstream, because we know that, for instance, the head loss is just equal to the pressure over, over pressure drop over the length of the fitting, which is input pressure versus output pressure over unit weight. So if you have a fitting, flow some water through it, measure the upstream pressure, downstream pressure. The difference in those pressures is how much pressure you're losing over the system, which is indicative of how much energy you take to have to pump stuff through it. So that's typically the way that would be measured. So not very different from what we've done. It's just that it's this magnitude here is an equivalent magnitude of a loss coefficient, K sub L. Typically, just like for major losses, the loss coefficient is a function of Reynolds number and geometry. But usually, this loss within a fitting is given just as a number. It's not given as a Moody chart. And the reason for that is there's assumption that the Reynolds number is greater than that needed for turbulence. So you remember in the examples, well, perhaps you don't remember in the examples we did, KL is equal to 1. It has no dimensions, right? This has no dimensions and this has no dimensions. So if V squared and 2G is the same as head loss in dimensions, then this has to be a non-dimensional parameter linking them. Typically, in these questions you've seen, it's a magnitude of 1, or 0.8, or 0.5. And so it's not 0.5 and changes its Reynolds number. And so the reason for that is it's assumed that the flow velocity is high enough that it just makes it, there's turbulence in the fitting, and so it doesn't change with the magnitude. In other words, if you were on this Moody chart, you'd be on this regime. So that's really all it's saying. And so also for flow in a pipe, if you're beyond this, this demarcation here into fully turbulent, the magnitude of the friction factor is always constant. It needs to get above this threshold before it's constant, so you need to know that Reynolds number. But once you're on the right-hand side of this, it's always the same magnitude of friction coefficient, which makes it a little simpler because you have to solve this equation. And of course, if you're solving this equation where the friction factor is a function of the velocities that you're traveling at, and you don't know your velocity yet, then you have to iterate on solving a problem. And so that becomes a bit of an issue. So it's actually very nice if you're in this regime to the right of here because you have a single magnitude of loss coefficient for losses in the pipe and also a single magnitude de facto for losses in the fittings. Okay, so I'm talking too much about this again. If you wanted to, sometimes people define the loss coefficient as an equivalent length of pipe. And if you want to do that, then we've just done this. This is the loss in the minor loss in a fitting. This is the major loss in a fitting. If you equate these two to each other, then what can you do? You can just get rid of this, and you can get rid of this. And if you rearrange it into an equivalent length of pipe, which is equal to the loss of the fitting, then it's just this. And so that's sometimes an easier way to think about this, is how much extra pipe do you fictitiously have to add to your system before you have the same amount of loss that you have in a fitting. It's sometimes just easier to deal with that way. And you can do that because the multiplier for both of these is just the same term. And so when we're dealing with these magnitudes of head loss, they're both dependent on this same term. Right, so this is minor, this is major. Okay, so I'm sure you all have that. So that's where we're going. And so you can imagine there are a variety of, so you can certainly measure these in some ways by measuring the pressure loss as you go across the fitting or the exit. There are two major kinds of non-fitting behaviors, and those would be when either you flow out of a tank or into a tank. And so we've always assumed that the losses here are zero when we've been dealing with Bernoulli for those questions. But you can imagine that as the transition from water that is going at zero velocity here and all of a sudden is not going at zero velocity here, you have to accelerate it. To accelerate it, you have to expend energy, and that's really what the loss coefficient is. And so, again, like when we talked about Venturi flumes or Venturi pipes, if you have the smoothest Venturi flume, you have the smallest loss because you don't have any flow eddies developing that eat up all your energy and that dissipate as heat. And so if you have a more disruptive fitting versus a really very straightforward fitting, then you could imagine that the loss that you have in the system is larger in the case where it's more disruptive. Less disruptive, at least you don't have a protrusion into the tank, so you don't have to go around here. You can physically go directly from here to here. If you round those corners, and if you round those corners even more, then you just end up reducing the fitting. And so you can imagine that as you make this transition more smooth, then going from zero velocity in a big tank, our big tank assumption, to going to some finite velocity, the loss magnitudes in each of these cases going from here to here to here to here reduce. So that's something that's worthwhile considering. And so you can imagine doing that as a function of the radius of curvature. And I won't talk about the vena contracta, but this is an exposition of this. If you have really sharp corners, in other words, where this radius of curvature is equal to some small number, so a small radius of curvature, I suppose, would look like this, then the loss coefficient is pretty big. When the radius of curvature is much larger, then the loss coefficient goes to something small. And actually, this is really just an exposition of these figures above it, right? This is the 0.5, which is the first number on that scale, and these are the numbers for progressively more rounded connections. Okay? So that's one. So the first one is if you're taking it from a tank, you're accelerating it as you go along a pipe, so it has to pick up some velocity, has to accelerate to that velocity, and there's some loss associated with that. Also, that we talked about this idea of friction, right? You're doing work against something. If I push my bag to the right, I've generated friction, I've lost energy. If I pull it back to its starter point, I net loss more energy to get it back to that same point. So if you start at zero velocity, accelerate along a pipe, and then flow into a big tank, again at zero velocity, then you don't necessarily recover that energy. You have losses in that case, not really due to friction, but by the fact that you've accelerated something, then decelerated, and you've lost those behaviors as pipe, as a function of changes in acceleration. And so the other behavior that is worthwhile noting for us is to think about losses that occur as you flow out of a pipe and into a tank, the opposite. Instead of accelerating up to a velocity in a pipe, doing the opposite, going from a velocity of something into the pipe and into stagnant fluid. And so in these particular cases, the loss coefficient that you might expect is that you're basically, it's like a stagnation point. This is the water flowing at some velocity. This is the, whoops, I guess I'm trying this. This is the submarine that's sitting in the tank, as we dealt with. And this is the stagnation point on the tip of the submarine, because the water coming in here into this big tank has to decelerate to zero velocity. And so different from the geometries with the tank that we looked at, where this geometry was worse than this geometry, which was worse than this geometry, and is worse than this geometry in terms of the losses as you go across it, they're all roughly equal to 1, which basically means that you're going from some velocity you have in the pipe to zero velocity. You're giving up all of that kinetic energy as you decelerate to zero velocity, and so there's no difference between those different geometries. So there's a slight mismatch. Flowing out of a tank into a pipe, there are different loss coefficients depending on the magnitude of the severity of this entry arrangement, and the reverse doesn't seem to make any difference, because in all cases you're going from some high velocity or some velocity to zero. Okay, so we won't belabor that point, but you could get magnitudes for that. So that's entry and exit losses. The other more usual behavior is to look at the response you'd have as you go around the fittings. So I've deliberately drawn this here with these magnitudes of the minor losses. But the other features you have, in addition to inflow or exit losses, which of course would occur at these points if you had them, then we have to worry about what the magnitudes as you go through individual fittings. And again, it's just a recipe. And so you need to go to whatever charts. Your book has some charts in them. The idea is as you go around a corner, you're certainly changing velocity, not necessarily speed, but you're certainly changing velocity. You may change the distribution of velocity in the pipe. And again, if you measure the pressure change between the upstream to the downstream, then empirically you can just measure the difference between these two pressures, which should be equal to the head loss, which should be equal to this coefficient, v squared over 2g. Typically this is the average velocity in some respects, right? So you get a a volumetric flow rate out of here. You divide that volumetric flow rate by a cross-sectional area, and you come up with some average velocity. Clearly the velocity in the center of the pipe is probably larger than the velocity at the edge, but we don't care about that. We're looking at overall flows in pipes. And in this case, to stop slippage occurring here, you have some vanes or flukes in here to be able to guide the flow around that don't go across the full width of the pipe, but just are in the wall to help guide it around. Part of the reason is that you have other kinds of bizarre circulations occurring, convection cells occurring as you go around the bend as well. And so you can get magnitudes of this loss coefficient as a function of, again, the relative roughness of the pipe. So high relative roughness, you have larger losses. Low relative roughnesses, you have smaller losses. And also as a function of the radius of curvature. If you have a large radius of curvature, then you're close to being a straight pipe, and so you're really not going around a bend. And so these magnitudes are small at this end of here for a large radius to diameter. And if you have a very sharp bend, so this would be this versus this, right? In terms of just the geometries of these. Not very good drawing, but you get the idea, I think, right? This is just radius, this is diameter. So it's a recipe. And it makes sense, right? I think. If the roughness is larger, you get more turbulence, you eat up more energy, and just as in the same way as on the Moody charts, that you end up being quite high up, this is a very rough pipe, this is a very smooth pipe, this is an infinitely smooth pipe with zero roughness, this boundary here. Then the magnitudes of the friction factor, which are proportional to the loss, are very small because you're down here versus being up here. And so it's just a natural follow-on from that. So it's hopefully it's very logical. I think it's quite logical. And this is taken from your book as well. Depending on the shape of the pipe, depending on the angle of the elbows, if it's 90 degrees or 45 degrees, depending on whether it's a threaded pipe, which has some extra roughness on the inside. So you might not really know the roughness of your fitting, but you might know exactly what it is in terms of its description. So it matters whether it's moving at 45 degrees, which are relatively small numbers, or if it's going at 90 degrees, which are relatively large numbers, except for this top one, I guess. Certainly this one, threaded. So if it's 45 degrees and threaded, it's 0.4. If it's 90 degrees and threaded, it's 1.5. You kind of expect that. You're just much more drastically changing the velocity in this pipe than you are in this one. If it's 180 degrees and you turn on itself, if you're going through a fitting as a T, where all the velocity is going in this direction, but there's a dead end here which is stagnant but still has a disruption to flow, you can imagine you might get some flow doing this as you go across here. Then there's also some loss in the fitting. If the fitting is open to flow, then the losses should be even larger. So I guess a T is when this is stagnant. A union, I guess that's not right. Line flow would be the top one, where you're just flowing past this opening, but there's stagnant water fluid in here, and there's no actual migration up here. Branch flow is where you actually go around a bend in addition to going through the fitting. And not surprising, the loss coefficients for going around the bend are larger than not going around the bend, so to say. And if you have a union between pipes, there might be a small loss as well. And if you have valves which are controlling the flow, these might be the valves where you flow in here, you go across here, this gets raised, so you unscrew this so that you open this little seal here, and so the flow through here is like this. Is that going through this valve, obviously you're changing the direction of flow, and in the same way you're also having some extra loss in the system. So it becomes just a game for the recipe of what your particular fitting looks like, what your valves look like, and you just sum up their individual effects in the pipe. So in that regard, it's moderately straightforward. Okay, let's do something with that. We said we were going to go back to here. Let's just break the recipe part and look at this. So what we are going to look at is how much power you need to be able, what size of pump you need to be able to size the engine for this. And I think it's a relatively straightforward calculation for us to be able to do. We need to make some assumptions about what's going on in terms of flow rates, I suppose, because we need the velocity through the system. And last year we spent much more time on this, but not so much this year. But you can come up with some estimates on what those flow rates would need to be based on how quickly you want to go and how high you want to go, etc. And so what we can do is we can just go back and do a quick calculation to be able to figure out exactly what the magnitude of the plant that we'd have to apply in this following on raft that follows these guys as they go across here. It's quite nice, quite an impressive piece of equipment, I think. It's kind of interesting. So let's do that. Where are we? So let's go to JetLev. So we are almost 2/3 of the way through, except for 10 minutes, I'm guessing. Pipe flow. So what we're going to do is we're going to take our guy, oops, I didn't do that very well. I'm going to have to go through his body. So that's kind of what we have, I think, right, in some respects. And so I suppose the important components of that really are just this tube. So if we simple this down to as simple as it can be, then we have this. We have an upstream, so I guess this is going to be 0.1. We have a velocity 1. We have this entry area here is some, not length, but an area, A1. We have a 0.2. And we have a velocity coming out of here, which is V2. Remember, for our Bernoulli equation, let's write that out also, is here. What is it? Elevation, upstream, pressure, upstream, velocity, upstream. Let's ignore the alpha value, plus the pump capacity, pump head, is equal to the elevation downstream plus the pressure downstream plus the velocity downstream. And let's write out the other components, just continue on this line. So the major losses are going to be friction factor, length over diameter of the pipe, and velocity in the pipe squared over 2g. So I'll just write them out, then we'll talk about them. And the head losses are going to be a loss times v squared over 2g. Okay. So let's talk about the important components. Let's put some numbers on this. I don't know how the guy was about 6 feet. Let's choose 2 meters just for laughs. Let's talk only about one magnitude of minor losses. And let's, for a right angle bend, it was of the order of 1, if you remember from what we did. Something of that. We have, a length of pipe. Of course, the length would be the whole length from point 1 to point 2, which I can't draw very well. And I pulled out some numbers. Yeah, which we can use. I don't know. Let's use 10 meters. That's 30 feet. Actually, it was almost that long. What else? We need some areas. I couldn't tell, but it seemed like the diameter of that was of the order of 4 inches. It probably was a bit less, but 4 inches is convenient because let's have the area A2. Let's have the diameter of the pipe and the nozzle be equal to 4 inches, which is 10 to the minus, which is 10 centimeters. And if that's the case, then the area is equal to that squared, roughly. I guess it's not exactly. You have to use pi in there, pi r squared. But it's equal to, or pi d squared upon 4. Pi over 4 is roughly 1. So it's approximately 10 to the minus 2 meters squared, roughly, for the nozzle, for A2. And so I don't know what the area for A1 was, but maybe it's of the order of a square meter, right? So you have this big raft following behind, it's sucking up water, and so the magnitude of the area of this, within an order of magnitude, is 1. And so let's figure out what we know in this particular case. The fluid here is basically on the surface, so it's pretty much at atmospheric pressure. So let's get rid of this. The fluid coming out of here is also coming into the atmosphere, pretty much at atmospheric pressure as well. So let's get rid of that. If we take our datum as z equals 0 here, then this one here is equal to 0. And then we just have to figure about the remaining components. We're going to have something for here. This is the velocity in the pipe. This is the velocity in the pipe. And let's have the velocity, the area of the pipe. A pipe is equal to A2, just because it's easy. Same as the nozzle. It'll make life easy for us. And so what's the question? The question is, how much power? That's a simple question. And so that's this. So we could rearrange everything in terms of that term. So the pump head that we need is going to be equal to, well, Z2 plus V2 squared over 2G. Okay. The other thing that I guess we need to know is how quickly it's coming out of here. Let's take V2 is equal to 10 meters a second. That's the other piece of information. We're going to take this magnitude off the left-hand side. We're going to subtract this, V1 squared over 2G. And we've already had this property here, and we have these losses, which are friction factor, length over diameter, times V squared over 2G, plus this loss coefficient, times V squared over 2G. So these velocities are always streamlined velocities, right? So we don't have to worry about directions. Importantly, these are velocities in the tube. If our nozzle is exactly the same cross-sectional area as the tube, then by definition, I suppose V is equal to V2. Because A is equal to A2. Right? That's just by continuity. So that's one observation that we have. So we could rearrange this, I suppose. We know this is 2 meters. We have this painful little thing here which we have to get rid of because all of these others are going to be in terms of velocity 2. And so what's that going to be? We could rewrite this as... so let's also note that continuity, what does continuity give us? It gives us velocity 1 times A1 equals velocity 2 times A2, right? This is just by looking at this. And so we have this pesky little velocity here that we'd like to convert into v2. So we can write that as velocity 1 is equal to velocity 2 times a2 over a1. And so we could substitute in here for that magnitude. And so I suppose by the same token, v1 squared and v2 squared is just equal to this. So we can make that substitution. So if we do that, let's try it. We end up with, I won't put the numbers in yet. This is z2. Oh, I've got plenty of time. Plus, all of these terms turn out to be functions of the velocity at v2. So in this particular case, not all cases, we can take that outside the bracket. And then we have 1 here minus whatever this term is here. It would be just a2 squared, a2 over a1 squared. All squared. We have this friction factor, which is going to be a loss. And we have a length over diameter. And we have a loss. So this is it. I think that's still okay. And so that gives us something that we know some things about. I suppose we have to choose some numbers for those particular parameters. How would we do that? Well, let's assume. So we know, what do we know? We know that this is equal to 1 because we've said that. We know that the length of to diameter is equal to what? Length to diameter is, the length is 10 meters, the diameter is 0.1 of a meter, so this is 100. Correct me if I'm wrong. We don't know what the friction factor is. Do I want to calculate that? I suppose we should calculate it, so we'll do that later. a2 over a1. So a2 is equal to 10 to the minus 2, a1 is equal to 1, so it comes out to be 1/100th. And so 1/100th squared, so this is equal to 10 to the minus, bless you, 10 to the minus 2 all squared. So it's going to be a trivial number. We can forget that. And the rest of these numbers we know because we have a velocity in this. So the only thing we need to figure out, I suppose, is the magnitude of the friction factor. And so what is the velocity is equal to, Reynolds number is equal to V times density times diameter over viscosity. Velocity is equal to 10 meters a second. Density is 1,000 water, 1,000 kilograms per cubic meter. Diameter is 0.1 meters. And viscosity is 10 to the minus 3 Pascal seconds. 10 to the minus 3 or 10 to the 3? Minus 3, right? So 10 and 0.1 cancel out. So it's approximately 10 to the 6. Great. Fantastic. So it's a magnitude of 10 to the 6. And so we could go back to our Moody charts. Hopefully that's equal. Choose a roughness. We didn't choose a roughness, but we could do. So we know that we're at 10 to the 6. Let's choose a roughness of, I don't know. Let's choose it smooth. So you've got a nice smooth pipe. Makes sense that you'd like the pipe to be nice and smooth. 10 to the 6 gives us a number, if we go off to this side, is roughly, since we're doing orders of magnitude, it looks like it's a bit bigger than 0.01, but let's use 0.01. Okay? So that's what we need. So Reynolds number, smooth pipe, it's turbulent or the transition, So the magnitude is this number. So it's 0.011, I suppose, right? But let's ignore the second digit. Oh, not that. Am I going to finish in time? And so therefore, friction factor is equal to 10 to the minus 2, right? 100th. And so if we put some numbers in this, then the pump head is equal to 2 meters plus, what's this? V squared over 2g. Velocity was 10 squared over 2 times 9.81 meters per second squared. It's roughly 10, right? Multiplied through by 1 minus 10 to the minus 4, a trivial number, plus 10 to the minus 2, which is this friction factor, times 100. Well, that's kind of convenient. I didn't quite plan that, but that's great. Plus 1. And so the pump head that we need is going to be equal to 2 meters plus 100 divided by 10 is 10. Divided by 2 is 5. And it's 1 plus 0 plus 1 plus 1. And so if you convert this, this gives you the pump head. And actually, we also know that pump head is equal to what? Number of watts divided by mass flow rate multiplied by G. Mass flow rate is going to be velocity times area times density. We know what G is. And so you can calculate that, what that comes out to be. I think if you do the calculations, I must have used the same numbers. It turns out that this is actually equal to, so this is equal to, so the bottom line. So in this, the pipe makes, if you calculate this out just in terms of heads, it's 2 meters plus 5 meters plus 0 meters plus 5 meters plus 5 meters. So this is the magnitude of the pump work that you get out of this. And so if this is equated to this, we can merely replace this as the power needed is equal to this term on the bottom multiplied through by these components. And so this would be velocity of flow at 0.2, the area of the nozzle, which is the same as the area of the pipe, the density of the fluid coming out of it, and gravity multiplied by 2 plus 5 plus 0 plus 5 plus 5. This is all in meters. And so what are these values? We said the velocity of water is 10 meters per second. We said the area of the nozzle is equal to 10 to the minus 2 meters squared. We said that the density of water, well, didn't say, density of water is 1,000 kilograms per meter cubed. And gravity is approximately 10 meters per second squared. So if you multiply those out, we have a 10 and a 10 here and a 10 to the minus 2. So these actually cancel out and give us 1. And so the multiplier is just 1,000. So the work, power needed, if you like, rate of doing work is given by this magnitude here, which is just 1,000 multiplied by these individual terms. Yeah, I guess all of them, right? 2 meters plus 5 meters the amount of energy taken to go into the pump itself on this large area, 5 meters and 5 meters. And so taken all together, then this is 5, 10, 15, 17, so this is 17 kilowatts. And so you're using 17 kilowatts to be able to run this. So 17 kilowatts is 170 100-watt bulbs, I suppose, and if you want to get some idea of the magnitude of the energy use used. So of this, if you had a perfectly frictionless system, then the only parts that you'd use would be by elevating the fluid to this amount and by increasing its velocity from essentially zero velocity to 5 meters, which are these two here. So this is increased velocity. So accelerate it. This is to elevate it. And so if you moved it at a very slow rate, then you'd only need to use 2 kilowatts. If you have a perfect system with no frictional losses, then you need, so if I just jump down one page, then this would be perfect system, and no losses, which would be 7 kilowatts, just the addition of these two. These represent frictional losses. This is in the pipe. This is in the bend, the fitting. The one fitting we assumed. If we had a second fitting, which you could imagine that we might do, if it really does look like this, that it's drawn so it has a bend not only here but also here, then you could imagine this being, in this particular case, being equal to 2 times this, which would be 10. So in our particular case, this extra portion is 5 kilowatts, and due to the fitting is 5 kilowatts. And so the total for all of these is 17. So it gives you some at least idea of the magnitudes of the power that you'd need, and therefore the capacity of the motor that you'd need to be able to drive that thing. Okay? So I'm going to leave it at that, and next time we'll talk about other ways of solving flow problems. It turns out that this particular one that we've dealt with here is the easiest of the forms of the flow problems, because you see that when we talked about this, we defined the velocities we need to go through the system. So as a matter of defining this velocity, we de facto, we know what the Reynolds number is within the pipe, and so directly, if we know the Reynolds number, we can figure out what the friction factor is. But if, for instance, you think about the behavior being defined in terms of an upstream and downstream pressures, where we have to solve for the velocities, then we have to actually iterate on the Reynolds number and therefore iterate on a friction factor. So that's our next challenge. Okay? So I'll leave it at that. Thank you very much.